In the previous topic, we teach convolutional neural network model for image recognition problems. Interestingly, we can also apply convolutional neural network model for natural language processing tasks. I'll give you a general introduction of applying CNN on NLP in this session. In traditional deep learning communities, a convolutional neural network is most commonly applied to analyzing visual imagery. For example, image recognition, facial recognition, and object detection. Most recently, convolutional neural networks have also found prevalence in tracking problems associated with NLP tasks by sentence classification, text classification, sentiment analysis, and text summarization. The concept of sliding or conversational, a predetermined window of data, is the central idea behind why CNN are named the way they are. An illustration of this concept is as below. Suppose we have the input sentence, "I like SP NLP workshop very much." The first thing to notice here is the method by which each word is represented as a 5-dimensional word vectors. We then apply 6 filters with 3 different kernel sizes, sliding vertically across the sentence one step at a time. Each filter is also composed of the activation function, similar to those used in feed-forward neural networks. Due to some mathematical properties, the activation function ReDLU is mostly used in CNNs and deep neural nets. Going back to image classification, the general intuition behind these filters is that each filter can detect different features of an image. The deeper the filter, the more likely it will capture more complex details. As an example, the very first filters in your convolutional neural network will detect simple features such as edges and lines, but the features at the very back might be able to detect certain animal types. All this is done without hard coding any of the filters. Backpropagations will ensure that the weights of these filters are learned from the data. The next important step is to calculate the output feature map from the convolutional layers. We will choose the maximum value from each of the output feature map, and this is called maximum pooling operation. Subsequently, we will flatten the pooling result into a fully connected layer and apply the softmax activation function to transform the fully connected layer to the 2-class classification. In this animation, we are going to show how convolution layer and maximum pooling layers works on natural language examples. Let's say we have 2 filters with kernel size of 4. These filters will slide vertically across the sentence and generate a 1-dimensional feature map with 4 values. Then we will apply maximum pooling layer to extract the maximum value from each feature map, and simply concatenate the 2 values as the pooling layer output. In this slide, we will show some code snippets how to implement convolutional neural network for NLP tasks in TensorFlow. We will use a sequential neural network model where we stack the network layers linearly. The work embedding will be done in TensorFlow based on our training datasets. In this simple network configuration, we perform 3 times of convolution and pooling operation in order to capture more features in the sentence. Finally, we flatten the pooling output to fully connected dense layer. and generate the classification output using softmax activation functions. Before we can train the neural network, choosing a proper optimizer is very critical. Optimizers are algorithms or methods used to change the attribute of our neural network, such as weights or learning rate, in order to reduce the loss function. Optimization algorithms or strategies are responsible for reducing the losses and to provide the most accurate result possible. If you can still recall, gradient descent is the most basic but mostly used optimization algorithm. It's used heavily in linear regression and classification algorithms. Backpropagation in neural network also use a gradient descent algorithm. When dealing with computer vision or natural language processing tasks, I want to highlight the Adam optimizer. The Adam optimizer works with momentum of first and second order, and it combines the advantages of two extensions from stochastic gradient descents. The intuition behind Adam is that we don't want to descend too fast just because we want to jump over the local minimum. We want to decrease the velocity a little bit for a careful search, in addition to storing an exponentially decaying average of past square gradients. Adam also keeps an exponentially decaying average of past gradients. The biggest advantage of Adam is that this method is fast and converges rapidly. And it also rectifies vanishing gradient problem and high variance problems. Text classification problems and algorithms have been around for a while now. They are widely used for email spam filtering by the likes of Google and Yahoo, for conducting sentiment analysis of Twitter data or automatic news categorization. However, while dealing with enormous amount of text data, model performance and accuracy become a challenge. The performance of a text classification model is heavily dependent upon the type of words used in the corpus and type of features created for classification. In this session, I'm going to teach you some practical techniques on improving NLP model performance. The first technique is always to pay attention to domain-specific features in the corpus. For a classification problem, it is important to choose the text and training corpus very carefully. For a variety of features to act in the classification algorithm, domain knowledge plays an integral part. For example, if the problem is sentiment classification on social media data, the training corpus should consist of data from social sources like Twitter and Facebook. On the other hand, if the problem is sentiment classification for news data, the corpus should consist of data from news sources. This is because the vocabulary of a corpus varies with domains. Social media contain a lot of slangs and improper keywords, which are absent in any of the formal corpus such as news or blogs. The second best practice is always use an exhaustive stop word list. Stop words are defined as the most commonly used words in the corpus. Most commonly used stop words are a, the, of, on, etc. These words are used to define the structure of a sentence, but they are of no use in defining the context. Treating these types of words as feature words would result in poor performance in text classification. These words can be directly ignored from the corpus in order to obtain a better performance. Apart from language stop words, there are some other supporting words as well, which are of lesser importance than any other terms. These include language stop words, location stop words such as country names or city names, time stop words such as the name of the month and days, and numeral stop words. As taught before, to have an accurate machine learning model, you must clean the training data beforehand. In most of the data science problems, it is recommended to undertake a classification algorithm on a clean corpus rather than a noisy corpus. Noisy corpus refers to unimportant entities of the text, such as punctuation marks, numerical values, links, and URLs. Removal of these entities from the text would increase the accuracy, because size of sample space of possible feature set decreases. Yet, it becomes essential to know that these entities should only be removed if the classification problem doesn't use these entities. For example, emoticons are important for sentiment classification, but may not be important for other text classifications. Feature engineering is another important part for machine learning models, but it doesn't mean that the more the features, the better. Keywords which occur in lesser frequency in the corpus usually doesn't play a role in text classification. One can get rid of these low-occurring features, resulting in better performance of the model. For example, if the frequency count of words of a corpus looks like the following, it is clear that terms fig and thou have occurred in low frequency as compared to other terms. Hence, if we choose a threshold of 10, all keywords with less frequency can be ignored, resulting in good accuracy. Corpus normalization will always help improve the NLP model performance. Words are the integral part of any classification techniques. However, these words are often used with different variations in the text depending on their grammar. It is always a good practice to normalize the terms to their root forms. This technique is known as lemmatization. For example, we have these words playing, player, plays, play, players. All can be normalized down to the word play as far as the classifier is concerned. Performance will be good when there is a single feature for 10 variations rather than 10 features for each variations. In some cases, features as the combination of words provides better significance rather than considering single words as features. Combination of n words together are called n-grams. It is known that bigrams are the most informative n-gram combinations. Adding bigrams to feature set will improve the accuracy of text classification model. Similarly, considering part of speech text combined with words or n-grams will give an extra set of feature space, also increase the classification model performance. For example, it is better to train a model such that word book when used as noun means book of pages, when used as verb means to book a ticket or something else. For deep learning model, the amount of training data directly determines the final model performance. However, it is very luxurious to annotate a large amount of training data. Data augmentation techniques are used to generate additional synthetic data using the data you already have. Data augmentation has been proved effective in computer vision, such as flipping, cropping, shifting, adjusting brightness, etc. However, it is not easy to augment text due to high complexities. Not every word we can replace it with other synonyms. Even changing the word, the context will be totally different. For NLP, data augmentation should be done carefully due to the grammatical structure of the text. In 2015, a computer scientist Wang proposed a novel method for text data augmentation, where they use k-nearest neighbor and cosine similarity to find a similar word for replacements. Leveraging this technique helped to generate lots of data in a short time. Alternatively, We can leverage pre-trained word embedding models such as Word2Vec, Graph to perform similarity search. There is another different approach which generates augmented data by generating it in data augmentation for visual question answering. Different from the previous approach, it doesn't replace a single or few words, but generate the whole sentence. The first approach is using template augmentation, which is using predefined questions that can use rule-based to generate an answer to pair with the template question. The second approach leverages LSTM to generate a question by providing an image feature. Please take note. The approaches that I introduced is designed to solve specific problems. If you understand your data, you should customize your own data augmentation approach. The last technique is called transfer learning, where a deep learning model trained on a large dataset is used to perform similar tasks on another dataset. We call such a deep learning model a pre-trained model. The most renowned examples of pre-trained models are the computer vision deep learning models trained on the ImageNet datasets. So it's better to use a pre-trained model as a starting point to solve a problem rather than building a model from scratch. Here comes to the end of topic 5. In this topic, we have learned the basic concept of natural language processing, various use cases of NLP, and various NLP model architectures. By the end of the topic, you should already be able to create an NLP workflow with text preprocessing pipeline, build a language model using bag of words, TD-IDF, or word embedding. You should also be able to apply machine learning and deep learning models to various NLP tasks, such as text classification or sentiment analysis. Last but not least, you also learn multiple techniques to improve the deep learning model performance for NLP tasks. We hope you enjoy the topic. See you next time.